this is connected particles part 2. So this goes over the next 5 questions. So this is all of these questions are going to be a little bit harder than the ones in the previous part. Question 6. So we've got a car of mass. There's a car 1,500 kilograms, and then it's towing a trailer of mass 1,000. Resistance forces of 200 newtons and 300 newtons. It looks something like this: 200 newtons resistance force on the car, and then 300 on the trailer, and we've got some tensions here in the tow bar between them. No, it's a rope, yeah, between the rope and between them. Given that the driving force is 750 newtons, determine the acceleration. So if we just do and also there'll be some drag here. But if we just do F equals ma on the full system, so we can cancel the tensions, we can do 750 take away 200, take away t, add t, so these two cancel, take away 300, will give you 250 equals the combined mass, which is 2500 A. Actually, ignore this resistance. I think I put this here because I assumed that there'd be another resistance, which would just be the friction between the road and the trailer, and then there should actually also be another one next to the car. But you can just ignore this because that isn't actually happening in this question, even though in real life there would be some friction between them. Anyways, yeah, so if you solve this, you get A is 0.1. Calculate the tension. You can just pick either this side or this side, makes no difference. But if you do this one, so 750 take away 200 is 550, 550 take away T equals 1500 A, where A is 0.1. Get T to be 400 newtons. Now we've got this other situation where now it's inclined on 5 degrees to the horizontal. So it looks something like this, and it's ascending uphill, which means we've got a new force acting that the car's pushing, and we've got the same resistance forces, which is what the question says. System moves with constant speed, and one thing to point out is say the acceleration of this one will be equal to the acceleration of this one, and the velocity of this one will be equal to the velocity of that one because they're connected. Anyways, yeah, so there'd be 1500 G acting down on this one here, and then there'd also be there'd be 1000 G here. Okay, now if you just do the triangle decompose this into its vertical and horizontal components, the horizontal component here is 1000 G sine theta, and then here it'd be 1500 G sine theta, where theta is just 5 degrees if you if you find this angle here, which will be 180 take away 5. Another way that you can think about it is that here they've got like a 90-degree triangle, right angle triangle, and if this here is 90 degrees and this here is 5 degrees, then 90 plus 5, and then you do 180 take away it to get that one. And then you've got that perpendicular angle there between the vertical component and then this horizontal, and so you do 90 plus this angle, and then you do 180 take away that to get the angle of that triangle there, this one here, and then you can just find what the horizontal component is. I went all over all of this in part 1, so I'm not going to do that again. But anyways, yeah, so like I said, that's 1000 G sine theta, 1500 G sine theta. Now, if we're having a look at the driving force, we can say that say if you do F take away 200, take away, actually no, is that what I looked at? For the okay, I think I looked at this one here first. So I did T take away 300, take away 1000 G sine theta equals the mass 1000 times by the acceleration. Now the acceleration here is just 0 because it's got a constant speed, so the rate of change of the velocity is just 0, which is the acceleration. Rearrange that for T, where G is 9.8. You'll get this. You could have also done it on no, actually maybe not that part because you don't know the driving forces yet. Yeah. Anyway, so you get this for the tension, a new figure for the driving force. Now we've got the tension, you can do F take away this, take away that, take away this, which we know equals the mass 1500 times by 0 acceleration. Just rearrange for F, you'll get this. We've got another situation, looks like this. So there's a car, this mass, trailer, this mass. We've got two tensions here, which we know. Resistance force 400, and then another resistance force here, 300. Let's just work out some stuff. F minus 300 minus 200 is F minus 500 equals the mass 1500 multiplied by the acceleration, which we'll just call A. We can find what A is in just a second. Have I found out yet? Okay, no, so I've just left that like that. It's because I actually had to use this one. It's fine if you work out something like this, because even if you do something like this and then you realize, oh, I can't go anywhere from this, it will become useful later, because once we find A, we can just use this to find F. Anyway, so if you look at this part now, you can do 200 take away 100, which is 100 equals 500 multiplied by A, and then you can just get A to be 0.2. Now we can put this back into there to get what F is, which is 800. You can leave that in there. The driving forces removed in the car's brakes are applied, providing a constant braking force of 400 newtons on the car only. So that driving force there is gone. We've got 400 newtons resistance only on the car. If you say have a look at this one, you can say that T minus 100 equals 500A. And now the tension is not going to be the same. It's going to be different because what is this? Yeah, so it's a turbo, okay. And so if we were applying a driving force forwards, okay, there'd be tension. But if say you're braking, you're compressing the turbo kind of, but obviously it's resisting that compression, and that resistance of compression is called thrust. In this scenario here, so you could say that T minus 100 equals 500A, and then you could also say here that minus 700, so minus 400 minus 300, so minus 700 minus T, and then equals 1500A. Okay, they'll have the same accelerations, so what I did is I just added them together, then get A to be this. You could have also just done F equals ma on the full system, by the way. You'd get the same thing. Anyways, you get the acceleration is minus 0.4 meters per second, but that means the deceleration is just 0.4 meters per second, so just be careful with that. Now put this back into any one of them to get the thrust, which is T in this case. You get minus 100 newtons. And also, so when I mentioned tension is like a pulling force acting on, say, a rope or any object. Tension is the pulling force. Now, if you had a negative tension, that's a compression force, and that compression force is the same as thrust. So if you have a negative tension, that just means thrust, or in other words, compression. So if you've got a negative 100, if you've got minus 100 tension, that's just 100 Newton thrust. Question 8. So you've got this situation here. We've got a driving force forwards, we'll call F, mass here of 2800, and then a mass here of 1200. We're told that cosine theta equals 0.75. You can say that this length, that this force forwards here, the horizontal component, is just t cosine theta. Okay. I've not split it up into the vertical component because you don't need to right now. But what we want to do is calculate the acceleration of the truck. Now, there are a few ways you can do this. I think I actually used Suva. Yeah, I did. Okay. Yeah. So I said that the final velocity is 27, and then the initial velocity is 12. The displacement is 2,340. Okay, and A is just A. So you just rearrange that for A, which is this. Okay. That's the first part done. Constant resistant force to the motion of the truck of 600 newtons. Okay, so we've got 600 newtons there, and we've got 270 newtons here. For the part of the journey which two vehicles accelerate, determine the force in the tow cable. Okay, so first of all, there's tension here. That's the force that it's referring to. Now, the horizontal component of this force here, just be a little bit careful. It's also t cosine theta, because here you've got alternate angles. So that means this angle here is theta. So you can draw a triangle here, and you can say that this horizontal component is t cosine theta. Okay, now we've got the horizontal components. We can just do F equals ma on the full thing. So if we do t cosine theta, what? Oh yes, I've just done it on this part here because, yeah, I've just done it on this part here. So I've said that t cosine theta take away 270 equals 1200A, but we know what A is. It's 0.125. And we know what cosine theta is. It's just 0.75. It says somewhere. Yeah, here. Just plug that in to get 560 newtons. And then I've done the same thing, but this time on just this recovery truck. So I've said that F take away 600, take away t cosine theta equals its mass 2800 multiplied by A. I've already said that cosine theta here is 0.75, and then the t is already 560. Rearrange for F to get 1370. Question 9. So we've got this situation here. Car and a trailer connected with it via a rope. Oh no, it's a tow bar, okay, rigid tow bar. So there could be thrust here, but this question is not talking about that. Mass of 1500, so you've got 1500 G acting down. Okay, that means the horizontal component here is what it's it's the horizontal component acting parallel to the inclined plane, 1500 G sin theta, and then here you'll have 600 G sin theta. You can draw yourself the triangle if you prefer. And what else can we say? So sin theta is 7/25, and we know that there's a constant resistance force of 400 newtons acting on the car, and then and also I've just replaced these because we know that sin theta is 7/25. And driving force here, and then the resistance force here 400, and then this other resistance force of 300. And I've just gone ahead and done F equals ma on the full system. So I've said the 8400 take away 400, take away 420G, take away T, add T, so these two cancel, take away 168, take away 300 equals the mass, which is 2100 multiplied by A. We know that G is 9.8, just get A, it's this. Just do as many decimal places, because say if you rounded this to 0.9, which is what I did in the first place, you'll get a different answer for the tension. That's quite a, big amount away from what the true answer is. So just do a few decimal places. The 6 here is actually recurring, but it doesn't matter. If you have a look at the car now, or you could just look at the trailer, makes no difference. To find the tension, we do 8400 take away 420, take away 400, take away T, equals 1500 A, where A is this. And you'll get 2500 newtons. Particles A and B, 2 and 5 kilograms. We're doing the exact same thing over and over again. This is 2G, this is 5G. We've got tensions here and here, and that's all we know for the right now. It's in rest, and it's released from rest. So for the period before B reaches the floor, calculate the acceleration of the system. Okay, using F equals ma here, we'll just say Fg minus T equals mass 5 multiplied by acceleration, and then we'll do the same thing for A here. So it's just T minus 2G. It's T here take away 2G and not 2G take away T, because the entire thing's moving up. Well, it would be moving up if it was here. Yeah, so before it reaches the floor, so yeah, this is moving up and this is moving down. So the resultant force is acting up here and it's acting down here. They'll have the same acceleration because they're connected. Just get what that is. It's 4.2, where G is 9.8, obviously. And just another thing I'm going to say is you could have just done F equals ma on the full system to skip these steps here and just get to this one and then work out what the tension is last time. I've kind of used like a mixed variety of say just the F equals ma on the full system, or just on individual particles over the last few questions. You can just use whichever one you want. It doesn't really matter in most cases. So you could have just done Fg take away T plus T take away 2G. Okay, so you'll have 5G take away 2G, which is 3G, and then equals the mass, the combined mass, which is 5 plus 2, 7 multiplied by A, and then you'll solve for A. I've just plugged this back into this first one here, where the G being 9.8 to get T, which is 28 newtons. I determined the greatest height. Oh, didn't actually mean to put that there. 1 second. Apologies for that. I had to get rid of that because that just spoiled the entire question. We want to determine the greatest height air reaches above the floor. This is very similar to question 6 that I think it was question 5 that we did in part 1. Anyways, we've got Suvat here, okay, and we want to find the displacement. Now you see, we don't know the displacement of B from the ground, or say from A to the ground, because it doesn't tell us it, but we can find it because we're given time. Okay, so if we say use this one here, because we know the initial velocity, because it starts from rest, so the initial velocity is 0. Okay, we know the acceleration, it accelerates down at 4.2 meters per second squared, and we know the time is 0.5, so just plug them all into this one here to get the displacement is this. So the displacement from here to the ground, or say from here to the ground, is 0.525 meters. Now, we could find the velocity that B hits the ground at using this one here, because we know that we can say that the final velocity is, well, we don't know what it is. We want to know what the velocity is as it hits the ground, not after it's hit the ground and it's and it being at rest now. But as it hits the ground, so the final velocity is just v, and the initial velocity is 0 because it's at rest, and acceleration is just 4.2, and time is just 0.5. Get v to be 2.1. Now, if this is accelerating down, so if this hits the ground at 2.1 meters per second and that's its final velocity, that's the initial velocity of v, or say of A moving up, but not from this point here. Okay, so B hits the ground with a velocity of 2.1 and it's traveled 0.525 meters. Okay, now A travels 5.25 meters up. Okay, and now the velocity down here is the velocity up here. That's the initial, and that's the velocity up here. Okay, we're going to call that the initial velocity, because like I said here, when B hits the ground, it's gonna like kind of jerk the entire system so that B moves up 0.525, but it's also jerked up a tiny little bit. And so if we add that to the total distance off the ground, we can find the greatest height it reaches. So now that A has already moved 0.525 meters up, okay, and now it needs to be jerked up a little bit. Now its initial velocity here, just before it's jerked, is 2.1, okay, and its acceleration after it, it's been accelerated up minus 9.8 meters per second squared, so it's going against gravity, okay, and its displacement is s, because we don't know what that is, and its final velocity is 0, because after it's already been jerked up and it goes back down, its final velocity is just 0 because it'll be at rest. Okay, plug that into this one here, solve for s, you get 0.225. That tells us that after it's moved up a little bit, this 0.525, it's jerked up 0.225 meters. Okay, and then it falls back down that 0.225 meters. But the greatest height it reaches is this 0.525 meters off the ground, and then this plus the 0.525 up more that it goes, because when this has gone down, this pulls it up, plus the 0.225 jerk in motion displacement. Okay, so add that again, add this is the greatest height, which is 1.275. This is the diagram that was on at the start, that was I accidentally put on. Hopefully that just shows you. Again, I went all over this in part 1, so this is kind of just a recap. But yeah, so this is its initial positions. It's already 0.525, moves up 0.525 when this one moves down 0.525, and then it jerks up a tiny bit there. Okay, that's everything. Thank you for watching.